Imagine a machine that could provide answers in minutes to problems that would take regular computers years to crack. Google, IBM, Microsoft, and scientists around the world are trying to make this reality by building the world's first quantum computer. It would be the biggest leap in computing since the computer itself. But what exactly is a quantum computer anyway? Here is a grossly oversimplified explanation. Physical objects like this apple obey certain rules, the laws of physics you learned in school. They move left and right, up and down. They collide, they bounce off of each other. But as objects get smaller and smaller, the laws of physics you learned in school start to go out the window, and quantum rules begin to take over. These tiny particles do all sorts of things we can't explain. They can act like waves instead of particles. They can instantaneously send information to each other over vast distances. But here's the main thing to remember. They can appear to be in two different states, or in two places at the same time. To understand how that can be used in computing, you need to understand how computers process information. Computers use bits. Bits are essentially yeses and nos, ones and zeros. Each bit contains one piece of information, like particles of information, following the rules of classical physics. But we can now build processors where the bits are single atoms. Now we're back in the world of quantum physics. At this scale, one bit of information could actually, amazingly, be a 1 or a 0 at the same time. We call these digital particles qubits. In theory at least, a computer made up of qubits doesn't have to work through each problem step by step. In effect, it could do all of the steps at once. It would be exponentially faster than the fastest computers in the world today, and do things we never thought possible. But barring some major breakthrough, it'll likely be decades from now before we start to harness the power of quantum computers. Qubits, by nature, are much less stable than traditional bits. They need to be isolated in large, expensive machines cooled down to extremely low temperatures just to work properly. And then there's another problem. Scientists have already built small arrays of qubits, but they can't be sure that they're functioning as quantum computers. The second you look at a qubit, it stops being in two states at once. That's just the nature of quantum effects, so you can't simply peek inside the machine to see what it's doing. A quantum computer is a black box, and it doesn't yield its secrets that easily.